Hello students. So I am starting a new lecture series for you, mostly for the BSc third year students, and this is in accordance with the syllabus of BSc third year, and the topic is very interesting if you study it properly and understand the concepts properly. And this is the electromagnetic theory. This is the most interesting part, one of the most interesting parts of physics and one of the most revolutionary topics in physics, that is the electromagnetic theory. This concept is the basis of the Maxwell's equations that changed the world of physics radically. And why it is revolutionary, we will study it later if you cooperate. So this is the basic syllabus of the electromagnetic theory, and it starts with the electrostatic potential due to a charge distribution, multipoles and their interaction with electrostatic field. Laplace and Poisson equation must be there, but they have not written the Poisson equation, so it doesn't matter. We will learn it what is Poisson equation. So now what we want to study, what I am starting with, is the concept of potential and the explanation of multipole expansion and the Laplace and Poisson equation. So what we will do in this section is that we will understand the concept of potential in a different way. Different way means the explanation of potential in terms of electromagnetic theory. This is the thing we are going to do here. Explanation of potential according to EM theory. According to EM theory. This is what we are going to do. This is the purpose. So let us start our discussion without consuming any more time. So basically, let us rewind some aspects, some concepts of potential. Now this word potential is known to you. It is not something which is unknown. You have been studying with potential from school level. You have studied potential in mechanics and most important in the electrostatics. So potential, the word is related to energy. However, the methodology or the way in which we are going to learn potential in this section, it will appear that this energy and potential relation is not proper, but I will tell you this is why it is so. But we have to accept this word and we have to go on working with it. So this is potential which is related to energy. Electrostatic potential, you know, it is defined as the work done in bringing some charge from infinity to a particular point, is the work done in bringing a charge from infinity to a particular point, that is the potential of that point. In bringing the charge, not the charge, a unit charge, or you can say for the time the charge, because I am using potential, the charge from infinity to that point. That is the potential of that point. So if you have a charge kept here and at a distance r, you have to find the potential. What you do, you calculate the work done in bringing the charge from infinity to this point r. This is in accordance with a particular coordinate system. The position vector of this is the point P, this is the point Q, and you integrate it E dot dr. Now this is the equation for potential. Now what we will learn in a different manner is that we will learn potential, we will define potential in terms of E, electric field. This is the definition of potential that we will consider here. And we will make use some concepts of vector algebra, and I feel that those simple concepts are known to you. If not, I have made lecture videos on gradient, divergence and curl, you can watch them. Or if you require new lectures, I can provide you. So, what we have to do, how we proceed in the formalism is that we make use of a very well-known theory. We make use of this condition, minus del V upon del R. That force is derivable from a potential. Now this del upon del R in the language of vector algebra, is called gradient, and it is very interesting and important topic. Most of the times it is taught in a very crude manner. Sorry to say that, but it is a fact. But if you understand this, this is a very interesting topic. Vector algebra is called gradient. Gradient means slope. Gradient means slope. So we know this formula from very beginning, from this equation. I will not use the word formula. This is the equation that we are using. So if there is a change in potential with space, this may R may be x, y, z, anything, or in any coordinate system. If it is changing with space, it gives rise to a force. Now by the similar formalism, we have the definition of electric field as E is dV upon dr, minus dV upon dr. This we also know. Or many times we write V upon d. So variation of potential with space. So this is the definition that we use. So electric field is the variation of, this is the definition of electric field that we will use. Variation of potential with space. This is the basic definition that we will use. Now let us come to our main discussion. Let us understand, or let us meet with potential in a different way. Now when we are talking about electric field is not just any vector notation, or it is not a ordinary vector function. Then what it is? What is the potential? It is a special kind of vector function whose curl is zero. This you must know. About curl, all things are very simple. Electric field is, we are defining these quantities in terms of some mathematical functions. Electric field is a vector function, that has zero curl. Curl means to turn. This is called curl. This is curling. Turning about a point. This is called curl. So in the language of vector algebra, what we write? We write del cross E is equal to 0. So it is a special vector function whose curl is 0. So from this definition, we have to find the definition of, or the concept of, potential. Now we are going to exploit this mathematical property of electric field to reduce a vector problem to a simpler problem. You know that vector equations or quantities that are vector, they are a bit complicated because we have to consider the direction also. With this definition, and this is a property of a vector function. With this definition, we will define a scalar quantity that is simpler to use. Quantity that is Simple. Because for vectors we have to take into consideration the direction also. Scalars are much easy to handle. What I mean to say is that we will make use of this function, of this special function e, whose curl is 0, to reduce it to a scalar quantity. This is what we are going to do. Now, from vector algebra, we will make use of one theorem. We will make use of one particular fact that any vector whose curl is 0, that vector is gradient of some scalar quantity. Any vector with zero curl is the gradient of a scalar. These concepts, curl, gradient, divergence, they are very important and very interesting. They are relating the scalar and vector quantities. So any vector E, if we have a vector E such that E has zero curl, del cross E is equal to 0, then it means vector algebra says E is equal to gradient of some scalar function. We are considering this function V for the time being. I am not defining its potential. Now your del cross E is 0, so this means you must have studied that the line integral of electric field of that vector function along any closed path will be 0. Work done in a closed path is 0. This we know from very basic physics. If del cross E is equal to 0, then it means that work done in a closed path is 0. This is the thing that we know from very beginning. Integral, closed path integral E dot dl will be equal to 0. And this type of problem, this fact we have come across many times. This is what is occurring here. So if there is any function whose curl is 0, then the work done in the closed path is 0. Now, if this integral is 0, the line integral, it is independent of the path. It depends on the initial and final points. For example, what I am trying to say is that if you have your starting point here A, and you are moving to some other point B, you take this path or you take this path number 1, path number 2, and you may return from B to A through this path. So the line integral is independent of the path. If you are going from A to B and then stopping there, then the line integral is not 0. But if you are returning to the initial point, then it means your initial and final points are same. So it is a closed path and your line integral is 0. Line integral is 0 means that the integral is independent of path. It depends on the initial and final points. It depends on initial and final points. This is the main concept. Because the line integral is independent of path, we can define a function of space, function of R, which is of the form. We can define a function which is an integral E dot dl from some reference point O to the point R, and we call this function as R. O is the point of reference. O is the point of reference. Now what does this equation mean? This means you are integrating this electric field, this force. This is similar to, or you can in a more easy way, you can consider this as F dot dr. This is force. Electric field is electrostatic force per unit charge. Force dot dr. What is this quantity? This is work. You are integrating from a reference point to a particular point of interest, and this integral, the sum of this force, this work is equal to some quantity which is a scalar. You are summing over the small amounts of work that is being done in moving the charge from O to R. And how do you evaluate the work? It is force times displacement, or the dot product of force and displacement. Here you have the force in the form of electric field, and dl is the small amount of path. You are going from O through small path lengths, and you are reaching this point R. The sum of all these works is equal to a function VR. This is what does this mean? And we have to define it with respect to a particular reference point, which is O. So this function V has the property that it depends only on this vector R, only on space, and this function is called electric potential. The function VR depends only on the quantity R, and it is called potential, not potential energy. They are different things. Potential and potential energy are different. This is called potential. Never write it potential energy. This is potential. So this is what we are getting. This is the definition of potential in terms of electric field. So we can easily define the potential difference. The meaningful sense of potential is accepted, or the meaningful sense is the potential difference. We are always defining potential as a potential difference. Potential is always expressed as potential difference. Potential difference. Many times we do not represent, or we do not show the reference point, but it is always a potential difference. So we can define VA minus VB as the difference of the integral from reference point to point A, E dot dl minus plus. So it will be reference point from 0 to B, E dot dl, and this is how you define the potential difference. You would evaluate the integrals, and finally it will be A to B E dot dl. So this is the potential difference. The difference in the work done in point A and point B. Now what is the work done? You bring the charge from the reference point to point A, some work is done. You bring the charge from reference point to point B, some work is done. This is W1, this is W2, simply this is W1 minus W2 in terms of work. That makes the explanation more easier. That helps in understanding the things easily. So this is what we are doing, this is how we are defining the potential. This is the potential difference. Now from the fundamental theorem of gradients, this is what you have learnt in class 12 or BSc part 1 or 2. Using the fundamental theorem of gradients, we can express potential difference as using the fundamental theorem of gradients, we can express potential difference as VB minus VA, the potential difference between 2 points, as the integral A to B E dot dl. In place of E we are writing del V, which is the gradient of a scalar quantity called the potential. Now you can call V as potential. This is nothing but E. We are making use of this thing. We are writing E dot dl in terms of del V dot dl because E is equal to del V. So this difference is expressed as the gradient of a scalar quantity. This is the definition of from now onwards. When you are studying electromagnetic theory, you define potential as the gradient of electric field. Gradient of electric field of E is potential. Gradient means slope of electric field. In terms of slope of electric field is the potential. This is what you have to define from now onwards when you are studying electromagnetic theory. So I think I am clear enough. And one thing that you have to always keep in mind, that potential and potential energy are different quantities. Potential and potential energy. Potential energy are different quantities. This you have to always keep in mind. Although the word is a bit confusing, they are different quantities. We will see how they are different. Now this reference point, I have told you in several other situations also, that potential, whenever you are defining potential is always defined with respect to a reference point. Potential is, in any case, even in mechanics, is always defined in terms of a reference point. In general, our reference point is infinity, where the potential is 0. Our reference point in general is infinity. Because this potential is always expressed as potential difference. This is always expressed as potential difference. So you have to have a reference point to define potential. So this is the concept of potential. Now one important property is that, and you know the unit of potential is volts. Potential also obeys, we will see from some example, numerical examples. Potential obeys the superposition principle. You must be knowing the superposition principle in electrostatics for electric field. So this potential also obeys the superposition principle. V is equal to V1 plus V2 plus V3. And when you are studying quantum mechanics, superposition is not something new to you. This is the definition. Now let us introduce ourselves to Poisson and Laplace equation. They are not very difficult, anything which is very difficult. So basically, Poisson and Laplace equation, I will just give you an introduction and the detailed theories will be given in the subsequent lectures. Poisson and Laplace equations. So what we have studied till now, that electric field is the gradient of a scalar which is called potential. Now if someone asks that what are the divergence and curl of E, we have seen that curl of E is 0 and divergence of E is rho by epsilon naught, where rho is the charge density. This is the form of Gauss law. If you are If you know this or if you have some confusion, then please tell me in the comment. I will try to make lecture videos on this topic also. So this is electric field, the divergence and curl of electric field. Now when we have defined electric potential, when we take this definition of electric field, when we define E as minus of del V, then what will be del cross E and del dot E. With this definition of electric field, what will be the values of these quantities? Now let us first check this del dot E. Del dot E will be equal to del dot divergence of electric field, and write electric field as del V gradient of scalar. It is minus del square V, which is equal to rho by epsilon naught, and this equation is called Poisson equation. This equation is called Poisson's equation. In the similar manner, if we have a situation where if rho is 0, we are in free space where there is no charge density, in that situation del square V is equal to 0, and this equation is called the Laplace equation. Laplace equation. These equations are of prime importance in studying electromagnetic theory, and we will study in detail the concepts and the most important thing, the potential due to a localized charge distribution and the multipole expansion. So for the time being, stay connected. This is a new lecture series. Let me know your decision, how you like it, which topics you want to study. That will be very helpful for me in deciding or in making the lectures, and it will be useful to you. So please stay connected with the channel, like, share and subscribe the videos. That will help you. Thank you.